Well, I want to welcome you to our summer alumni event. It's supposed to be in the spring, but we kind of got delayed a little bit. But I want to welcome you all here. What do you think of the venue? Is this great? You know, now we bring together physical sciences, engineering, and information and computer sciences together. We bring all our alums together. And I don't know if you all realize how profound that actually is. For a number of years, the three deans of those schools were always scheming and plotting against each other, literally at each other's throats. And in fact, the dean of information and computer sciences and the dean of engineering oftentimes would not even be in the same room together for, you know, this whole thought that a fist fight could literally break out.
There was a rivalry.
Needless to say, all talk of fighting stopped when I was hired. And this is just one venue, one thing that we have going together. There are just a whole host of others. I see both Marios and Ken as my partners in crime as we go forward and not just put on these events, but we're really taking science, technology, engineering, and mathematics to a whole new level at the institution. And we're starting to see the fruit of that, not just in the area around UC Irvine, but really we're affecting the whole state and the whole country. And so it's just a really, really good thing to see. This event could not have happened without the hard work of some really dedicated people. I want all of the staff in engineering, information and computer sciences, and physical sciences. So please stand and formally be recognized. Where are you? There you go. Thank you. Most importantly, it could not have happened without the real dedicated work of Kristen Hirth. Where's Kristen? Kristen, raise your hand there. She is in the back. We're literally just sitting here talking about this and saying, okay, you know you got to top this the next time, right? And, I mean, how do you do it, right? We just had, a number of us just had this tour by Dr. Ed Krupp. I don't know if Ed's here. Is Ed here? I don't see him, but the tour that we got from the folk here at the observatory was just simply outstanding. A piece of American history is right here in this place, and I hate it for me personally that it's taken me this long in order to get here, and so it is just fabulous, and I'm really glad that we have all of you here to share it with us. I'm supposed to tell you a little bit about what's happening in the School of Engineering, and I want to highlight that as we speak to you today. I will tell you, so I've been here now, this is going into my 8th year. I actually, myself and Dean Janda are the two longest serving deans at the university right now. I think we both started at right around the same time, and everyone else has been fired or quit. So we're still standing.
What are you saying?
But I will tell you, I will tell you that this year for engineering has definitely been the best year since I've been here, and maybe one of the best years in the history of the school. Any major metric I point to is up and up significantly. We're approaching 5,000 students now. About 4,000 of them are undergraduates, and about 1,000 of those are graduate students, which is the largest we've ever been. We're also impacting more students in the state than we ever thought, not just in terms of sheer number, but in terms of social and economic backgrounds. About 34% of our students are first gen, another 28% of those students are low income. And so we're really impacting this community where it matters. And I say that all to say that we also just took in our brightest class of students on top of that. Our average entering GPA was a 4.1 this past year. And I will tell you, I went back and looked at the stats of most of you all in this room who are engineering graduates. You would not get in. Be thankful you applied when you did. Because you would not get in. Here's the interesting thing. I would not get in. And I tell the students that all the time. We're the campus now, UC Irvine in particular, we're a destination choice for students. Overall, when you look at the amount of students who apply to the University of California schools, we came in second next to UCLA in terms of students throughout, and that's more applicants in Berkeley, that's more applicants in Davis, there's more applicants in San Diego. And if you take it one step further, these 3 schools make up about 25%, well, a little over 25% of the applications to the university. And so that's a big deal. So, yes, you can give a round of applause for that. This year we brought in our largest class of new faculty. We've hired 15 faculty members. 6 of those are women or underrepresented minorities, which is a big deal for us. Since I've been here now, we've hired 19 women on our faculty. Out of the 53 people we've hired, 19 women and 9 faculty from underrepresented groups. And that's a really big deal considering how difficult it is to get those individuals to join. It's good. Our research went up somewhere in the neighborhood of about 20% in funded research expenditures this year, and new awards, meaning the next set of expenditures are going to be even greater. We're up about 45% there. And our future just looks incredibly bright. We're building arguably a new entity on our campus that brings together our 3 schools in a very, very unique way in our interdisciplinary science and engineering building. That facility will focus our faculty not just on, it won't be just a place for our faculty to come together and congregate, but it will focus them on the problems of the future. Really what we call grand challenge problems: water, energy, health, medicine, really big challenges that have been very difficult to solve. We think that if you put the right people together and you put them in the right infrastructure and facilities, that those people can come up with breakthroughs and tremendous outcomes. And we're building a new interdisciplinary science and engineering building to do that. That building will be somewhere in the neighborhood of 120,000 square feet, and construction on it, groundbreaking has already happened, and formal construction will begin in a couple of months. And so it's really good to see that happening. And then finally, as we grow our student body, we're actually expanding and changing and putting in place new departments. And this year, we formally reconstituted or split our chemical engineering and material science department into 2. So we now have a chemical and biomolecular engineering department, and now we have a material sciences and engineering department, which puts us on par with large research engineering programs of our size. And so all of that continues to happen. And then the last thing I'll leave you with is that we're getting lots of support from our external donors. That interdisciplinary science and engineering building was brought about by a $30 million gift from one of our benefactors. And we just recently received from another company, Horiba, a $9 million gift to establish a next generation institute on mobility and connectivity. That's going to help us usher in this whole idea of making Irvine one of the quintessential smart cities in the country. And so it's just a lot of good things happening. I look forward to great things happening. I will tell you as I leave the stage that, and I say this every year, and I say it because I mean it, the value of your degree You know, many of you, when you were at Irvine, it was a small, sleepy place. Not anymore. The value of your degree has never been worth more than what it's worth today. And I can guarantee you that the value of that degree a year, 2 years, 3 years, 5 years from now, it will be worth much more then than it is today because of the great things that our faculty and staff are doing. So now I'm going to invite up Dean Marios Papa FMU, and it took me about 3 months, but I can finally say that and roll it off my tongue for the School of Information and Computer Science.
This was perfect, by the way. Even I cannot pronounce my name. So. You must have been practicing really hard. You can tell. Greg mentioned that we cannot be. The deans couldn't be in the same room together. Now we can be in the same room, but we're still keeping some distance. We're not sitting right next to each other. Just to be safe. It's really exciting to be here with all the alums tonight. Not only the ICS alums, but also the engineering alums and the physical sciences alums. I've been at UCI for only 18 months now. So I'm still thawing from my 20 years at the University of Michigan. And, Michigan was a place where alumni was a big part of the picture. Once a student, you're always a student there. And I really, really excited that I see more and more of this alumni collection building up among the UCI alums. You don't really realize that you're the live advertisement of what we do. Yes, our faculty are doing excellent research, our graduate students are doing phenomenal research, but it's really the alumni who are there for many decades now, 5 decades at this point, who are the live, marketing for this place, if I can say that. So, really excited to be in events like this. Let me tell you a few factoids about ICS, and then I'm going to pass the baton on to my friend Ken Janda. ICS has been exploding, even before my arrival. It all started 5 years ago, and as of fall 2018, we have a record number of undergraduate students in the school, 3,500. Those of you who remember ICS in the 80s, I think the class size was 24, 25. I mean, these are the numbers I hear. The class size these days is 800, 900. I go to commencement, and after an hour, my right hand is hurting. I mean it, right? Try 800 handshakes in an hour. It's a lot of hard work. So 305,000 undergraduates. The computer science major is the largest among all the majors in the school. At this point, it's the third largest program on campus. Applause, please, some of them. Our data science major is the fastest growing major. It's not the largest yet, but it's growing by leaps and bounds. We have 100 students, and it's only in its second year now. Graduate enrollment, we have more than 600 students at this point. About half of them are in the various PhD programs. The other half is in the master's programs and the professional master's programs, which we started a couple of years ago. There's a professional master's degree in computer science, a professional master's in human-computer interaction and design, and there's 2 more in the pipeline, one in software engineering and another one in data science. So these professional programs do not pretend to prepare students to do research. They prepare students to go back to industry if they come from industry, or they prepare them to enter industry. So we've been doing very well on that front. Rapid growth, but I must say that the program is becoming more and more selective. For fall 2018, can you guess how many applicants we have? Freshmen and transfers. Do I have a number?
9,000.
9,000, do I have a number?
8,000.
8,000 are here? 10,000? 70,000? No, it's not 70,000. Now they can rule out. So you're quite close, actually. The number was 10,000 and a few hundreds. That's a record number. These are 10,000 applicants. Now the thing, that's the denominator of the fraction, and unfortunately the numerator is a much smaller number, the number of positions that we had in the school. These 10,000 students competed for 700 positions. I know, it's brutally competitive, and the program has grown by a factor of 2 within 5 years, which by academic standards is, it doesn't get faster than that. Nevertheless, the demand is up there, and we're doing our best to get as much of that demand served as possible. We have the highest SAT scores. I'm sorry, Ken. The highest SAT scores on campus among the incoming students. We don't have the highest GPA because engineering has the highest GPA by 0.01. So engineering beat us by 0.01. NSF graduates, fellows, Google fellows, long list of accomplishments. So yes, we've been hiring a lot of students. Lots of faculty with those students. We are at record levels. We hired, during my first year here, it was not all my doing, a lot of stuff was happening before my arrival, but in 2017 we hired 9 new faculty, including yours truly. This past year we hired 12 new faculty, and we're going for another 12 next year, and another 12 the year after, and there's no end in sight. The school is growing. These are not replacement slots. We are at almost 90 tenure track faculty, more than 100 if you include the lecturers. So there is enormous growth, explosive growth. If you ask about areas of research, we are piling up on the traditional strengths in machine learning, data science, big data. I mean, we think it's a fad. I don't think it's a fad. There's more and more data coming at us. If you have good ways to deal with it, there is value. If you don't, you're left behind. So we're making a big investment in big data. Human-computer interaction, which is another area of traditional strength. There's a lot of interest in that area. Cybersecurity. We cannot live our digital lives without a secure environment. We're arguably the best place in the country for digital media and learning. And you will ask, what is digital media and learning? It's really the whole art and science of getting computing and information to teach us in whatever modalities that happens, whether it's computer games, whether it's educational programs, what have you. IECS right now is a powerhouse in this area, and a lot of exciting stuff is happening in that space. I will, I have 3 minutes, I used at least 7. Yeah, I have a
Yeah, we do have a lecture.
I know. But I want to leave you with 2 tidbits. Tidbit number 1, very exciting that we have an interdisciplinary science and engineering building coming up. My 2 other partners in crime are sitting there. I think it's even more exciting for our faculty and even more exciting for our students. So we broke ground a month and a half ago. Fall of 2020, we will be into our new building. So that's very, very exciting. Last tidbit, pull out your calendars, your Palm pilots if you are from the 90s. Your Newtons, does anyone have a Newton in it? It was my favorite toy. But pull out your calendars. ICS is celebrating 50 years. Okay? The program started back in 1968 as a department program, some sort of an entity that floated around for almost 30-something years. 2002 it became a school. 2018 we're celebrating 50 years of ICS. So big hoopla. There is a day. You must have received email. If you haven't, then it means that our email lists are not doing what they're supposed to be doing. October 16th. Are you taking? October 16th, it's the day-long event at the Beckman Center, starting tennis in the morning and going all the way to 9 p.m. It's going to be a day-long celebration of 50 years of information and computer science excellence in research and teaching in the University of California, Irvine. The stage is going to be almost exclusively alums. I made a point that I don't want non-alums to be on the stage unless they're faculty who sort of have to do that. But we will be parading a small subset admittedly, but still many very successful alums giving the landscape, the history of the place, and also looking forward, telling us about all the exciting things that they're doing out in the real world, either in industry or in other academic settings. 2 exciting keynotes, one on artificial intelligence at noon by Professor Pedro Domingos. He's an alum from UC Irvine. He's now a professor of computer science at the University of Washington. And then the keynote for the day, Vince Steckler, who's the CEO of Avast Software, another alum from the 80s. He's going to talk about UCI and IPOs. So it's going to be a super exciting event, memorable event. Please mark your calendars. I look forward to seeing you there, and I look forward to hearing what Ken has to say.
So let me just start by saying I'm so delighted that so many of you have come to celebrate STEM learning at UC Irvine. So I understand some people came down from the Bay Area and all the way up from San Diego. Did anyone come from further than that for this? Where'd you come from? New York. New York. Indiana, okay. So I hope that this is a sign that UC Irvine STEM education is now, as Dean Washington said, inclusive for your whole career. How many of you took classes in the School of Physical Sciences when you were students here? I bet everybody, right? Who's alum. And we give a quarter of the freshman and sophomore grades on campus. We only have 2,600 majors, compared to these two guys, because, we're the fundamentals. But how many people are math majors? We now have 1,200 math majors. So just to see how things have changed. And I'll just point out that I'm so old. When I was in high school, there was no such thing as 4.1. So I'm pretty sure I'm the oldest person on the faculty here tonight. So anyway, the School of Physical Sciences is absolutely delighted to be teaming up with the Henry Samueli School of Engineering and the Donald Bren School of Computer Science. I think the three schools make a heck of a team. This new building is going to be great. It's going to emphasize saving personal lives, molecular medicine, biomolecular engineering, personalized data science applied to medicine. It's going to save the world. It's going to bring clean drinking water. One thing you may not have thought about, certainly our president hasn't thought about, there's more fresh water now flowing into the Atlantic Ocean from Greenland than from Brazil. Think about that for a minute. So Dean Washington mentioned grand challenges. So these are grand challenges that we're going to work on together with your help and with your encouragement. If you want to join our student mentoring program, we'd love to have you do that. So, but you didn't come here to listen to me, so let me introduce our featured speaker tonight. Professor James Bullock came here in 2004, and he is the founding director of the UCI Cosmology program. 2 deans ago, Dean Ron Stern really wanted to raise the astronomy impact here in Irvine, down in Irvine, and James was a big part of that. Aaron Barth here tonight? Over here. So he was part of that. I think we hired 5 people that year in cosmology, and you're going to see what a profound impact that's had, because he's a spectacular lecturer. So just a little bit more about James. He was an undergrad at Ohio State, graduate student at Santa Cruz, which is one of the world centers for observational astronomy. He understands galaxy evolution, but why should I tell you about him? You've got the real person. So let's welcome James Bullock.
Thank you, Ken. Let's make sure this is on. Okay, is it on? Yes, good. Thank you, Ken. Thanks everybody for being here. Boy, it's already been so much fun just to get to be here and watch what's going on. And I am really excited to come and tell you a little bit about some of the stuff that I do and the research that I'm passionate about. So the title of my talk is Biography of the Milky Way. And what I want to tell you about is a story. So a story about how we think our galaxy evolved and came to exist. I'm actually really happy to do that. I've been chair of the Physics and Astronomy Department for the past year, and as part of that, I get the great pleasure of going around and trumpeting all of the awesome things that people are doing in all of the Physics and Astronomy Department. But because of that, I don't get to talk very much about my own research, which is really what I love to talk about. And so I'm going to indulge myself tonight and tell you mostly about stuff, or at least interweave into this story some of the things that I've been working on and what I'm passionate about. So I really love this picture. So this is a picture of the Milky Way seen over Easter Island. And I think it really brings to life, it sort of calls to mind this idea that no matter where you are in the world, or even when humans were looking up at the night sky, we look up and we ask ourselves, what is this? What is this that I'm seeing? And one of the most profound things that we've discovered in the last 100 years or so as astronomers, and in fact, most of that discovering was done right here in Southern California, is that we inhabit a galaxy, the Milky Way galaxy, and that galaxy is just one of hundreds of billions of other galaxies that are strewn throughout the cosmos. So the story of how that Milky Way got here, how we emerged here, is what I want to talk about. So here's another picture. Again, the Milky Way stretched over Easter Island. And this is what we see. If you go out to a really dark place, like an island in the middle of the Pacific Ocean with no light pollution, you can see the Milky Way by eye. And it's just an amazing thing, especially when you realize what it is you're looking at. Because what you're looking at is the edge of a vast disk of stars that we live within. So the disk is fairly thin compared to how wide it is, and so you look at it, you see that dark stuff along the edge, that's dust in the Milky Way galaxy that's casting a shadow from the stars behind it. So it's this amazing thing. Now, we live about halfway out, just on outside of a sort of normal spiral arm of the Milky Way. And the galaxy is huge. It's a really huge collection of stars. So to put it this way, if you took the Milky Way galaxy and you scrunched it down to the size of the Pacific Ocean, then the entire solar system, okay, I'll give you Pluto, all the way out to Pluto, okay, is a maple leaf floating on the ocean. Now imagine a bee sitting on the leaf. The sun is a tiny piece of pollen on the leg of that bee. And the Earth is microscopic. Okay? So that's our galaxy. And when you look at the night sky, even on a really dark night, you see so many stars. And you're like, oh, it's countless. So many stars. The universe is so big, right? It brings this to mind. But in fact, every single star you see by eye at night is inside that bubble. And the only way you can see beyond it is you need instruments. You need telescopes. You need to peer using light other than visible light to try to sort of look out and map out the galaxy. If you put it in astronomer terms, or slightly more, try to measure it, the galaxy is about 100,000 light years across, right? So traveling at the speed of light, it would take you 100,000 years to cross the galaxy. In total, there are about 200 billion stars in the galaxy, and we think that among those stars, in fact, orbiting almost every star are planets, but in fact, we think among many of those stars, about 20% of those stars are habitable planets. That is, planets that are rocky like the Earth, that orbit at the right distance from their host star, to potentially have liquid water. So you could imagine these planets being habitable. 40 billion. There's about 10 million black holes. There's a supermassive black hole that lives right in the middle of our galaxy. It weighs millions of times the mass of the sun. So it's just this amazing collection of stuff going on in the galaxy. And of course, on at least one of those planets, we have people who look up at the night sky and ask why. Oh, and by the way, there's 100 billion other galaxies like this out there in the universe. Okay. Now, when many people hear this number, it makes them feel insignificant, right? But I don't think it should make you feel insignificant, because you're a member of the species who figured this out. Floating on that leaf, on that giant ocean, in a blink of time compared to the age of the universe, we've managed to put this story together thanks to the combined efforts of basic science but also technology, right? Because if it wasn't for the advancements of telescopic technology, we wouldn't know any of this stuff, right? So it's this global effort. So let me go back to this picture, right? So one thing I've done is I've circled a couple of other things up here in the sky. These little blobs, right? They look like little pieces of the Milky Way kind of broke off. They look like clouds. From the southern hemisphere, you can see these by eye in a dark place. These are called the Large and Small Magellanic Clouds, and they're in fact satellite galaxies of the Milky Way. So if you were to zoom out from the Milky Way disk by about a factor of 10, you would see that we don't live alone. The Milky Way has a couple of, in fact, several little galaxies that orbit around the Milky Way. Most of them are way too faint to see by eye at night. They've only been discovered actually fairly recently. And we have a sister galaxy called Andromeda that's about the same size as us, that's about 2.5 million light years away from us. And it has its own sort of network of little satellites that orbit around us. And if we zoom out another factor of 10, we see that we live in this structured universe, right? So the universe on the largest scales is a universe of galaxies, and it's not sort of randomly distributed galaxies. These galaxies sort of are networked together in filaments and clusters. This thing right here is called the Virgo cluster. It's the biggest cluster of galaxies that lives around us. And if you were sort of zooming through the universe at speeds much faster than the speed of light and trying to figure out where the Milky Way was, you would orient yourself against this signpost because we live sort of in the outskirts of this big zooming, booming metropolis here of Virgo that contains thousands and thousands of galaxies of its own. So how did this happen? Like, what's our story here? So I've just told you what. And what I want to do now is talk a little bit about how we think this all came to be. And this is a story, of course, that's continuing to evolve, but I want to tell you sort of what we think now. Okay, so we have this model of cosmology, and I'm going to call it Big Bang Cosmology. And it's in this picture, and there's tremendous amount of evidence that something like this happened in the history of the universe. About 14 billion years ago, everything we know of in the universe today was scrunched down into a volume that was much, much smaller, much, much hotter, and in fact, much simpler. So about 13.8 billion years ago, everything was hot, much hotter than it is now, almost featureless, so perfectly smooth, and contained only simple atoms, incredibly simple atoms like hydrogen and helium, things that make chemists very bored because they don't do anything. You can't do anything complex. Okay, sorry, Ken. I'm just insulting people who study hydrogen. So it starts out with all this simple stuff, right? Nothing really complex. And it's been expanding and cooling down since this time. But out of this very simple start emerged all the complexity we see around us today. That map of galaxies, the galaxy itself. And so the question is, how did this happen? Well, one of the things that happens is gravity. So that's something we understand pretty well. And if you start off with a distribution of matter that's fairly smooth, and you just let it evolve, if there's any imperfections in that early distribution of matter, it will begin to clump together because gravity sort of is it ultimately wants to make denser things denser and less dense things less dense. And so, in fact, this is what used to be considered a big supercomputer simulation. You could probably run this on your iPhone now. Of a distribution of matter, a big chunk of the universe, and how we think it evolved over time. And one of the things that's very interesting is we seeded this with initial conditions that look like measurements of what we think the early universe looked like. And over time, even though it started off very smooth, it turns out it started off with imperfections at 1 part in 100,000. It emerged to create a universe that was very clumpy. And the way to think about this is these yellow spots are spots where we think galaxies are going to grow because things get very dense there and gas can start to form stars. And then there are these big empty bubbles that surround those regions. And so you can imagine a system like this is going to be a galaxy cluster like Virgo, and out in the outskirts is something like us, like the Milky Way.
What's the rest?
The red is even denser. So this is even a crazy denser thing that emerged. So yeah, and that's very rare, turns out. And what's amazing is if you put together these kind of computer simulations and you compare them to the real universe that we see that, in fact, it looks incredibly like the universe that we observe. So this is actually a map of the real universe. Every dot is a galaxy. This map stretches 2 billion light years across. And you see that there's these sort of networks of filaments and sheets and this kind of complex structure. It's not random, right? The galaxies are distributed in a way that has structure. And in fact, the simulated universe is something that we sort of understand how this structure emerged. It started off smooth and got clumpy over time. And in fact, you even see this a little bit here. As you go out this way, right, you're going, the sun would live here in the middle. We're taking surveys going out. So imagine you have a telescope that's sort of carving out a triangle in the sky like that, and you're mapping things along. So at this edge, you're seeing galaxies that are farther away. You can begin to convince yourself that the structure is a little less here than it is in here. That you see some changes in the universe over those timescales. It's not a big effect, but it's a little effect. So we have this picture of the universe, this sort of story of cosmology, where the universe began with a bang about 14 billion years ago. And it began smooth and very simple. And the only elements that existed in the early universe were hydrogen and helium. And over the next sort of billions of years, eventually galaxies form, a galaxy like the Milky Way. And on at least, and this galaxy is filled with stars, hundreds of billions of stars. And on one planet, very interesting and complex things happened. So the stars that formed throughout this time, right, made heavier elements, fused these light elements into the heavier elements that are required to have things like planets. So there was no carbon, nitrogen, or oxygen in the very early universe. That took stars and supernovae. That is, when stars get really massive, they blow up as supernovae and create even heavier elements from fusion. So all of that stuff happens, and the galaxy kind of traps all that stuff. It's like a cocoon or a nursery that holds on to all those precious, more complex elements. And eventually, on at least one planet, we have enough carbon, nitrogen, oxygen, and life emerged. Yes. She doesn't look like that anymore, but I still like that picture. So the title of this talk was Biography of the Milky Way. And so, what is the story of the Milky Way? Like what happened? So if we think about all the stuff that eventually made the Milky Way and all the stuff that became it, what was it doing? What was its story? One thing that's pretty clear, humble beginnings, right? So in a biography, we start at the very beginning, definitely a humble beginning story, rags to riches story. 0.001 seconds after the Big Bang, everything that would become the Milky Way, the Milky Way, of course, did not exist yet. There was a tiny patch of the universe that would eventually become the Milky Way, but it really wasn't distinguished from the rest of the universe yet. It was almost indistinguishable from the rest of the universe. It would be very hard to measure the difference. But the protons that would eventually make everything in the Milky Way did exist then. They had, in fact, just emerged from the primordial complexities that happened in the early universe. Matter and antimatter had annihilated and left matter. So the protons were there. All of that material that would eventually make the Milky Way was compressed into a volume that was 100 million billion times smaller than the Milky Way is now. It was scrunched together, right? So that's like taking that whole Pacific Ocean of the Milky Way and crunching it down into the Earth. That is a microscopic scale, like smaller than a grain of sand. Just incredibly dense, right? Now, of course, if you take that much water and crunch it down into something the size of a grain of sand, it's not going to be water anymore, right? It's going to be a very complex thing, sort of like a plasma, but not even made of normal atoms. So that's sort of what you had going on, like a crazy plasma like that. And again, like I said, other than this little region eventually becomes the Milky Way, it's very difficult to distinguish it from anything else the Milky Way becomes. Flash forward 400,000 years later. What's going on? Finally, we have some atoms. Those protons have turned, we now have some neutrons and protons. They've combined together, and there's some helium and hydrogen, and they've become neutral. They've even captured their electrons, and you have neutral atoms. And the region that's become the Milky Way is finally starting to differentiate itself from the rest of the universe. It's actually starting to, it's expanding. The whole universe is expanding, but it's starting to expand just a little bit slower than everything else. And so eventually it's going to stop and recollapse and begin to form something. About 200 million years later, that's when the first stars start to form that are eventually going to be part of the Milky Way, or at least contribute heavy elements to the Milky Way. These first stars that form actually don't live very long. Right? They only live 1 million years, which is not very long. Okay? And they blow up. And after they blow up, they spit out all these heavy elements like carbon, nitrogen, and oxygen back into, and iron, back into the sort of general surroundings that are incorporated in the next generation of stars, which actually live much longer, many of which can live billions of years till today. Finally, 9.2 billion years after the Big Bang, that's when the sun forms. And a short time after that, the Earth. Okay? And the disk of the Milky Way had probably emerged by that time. So the sun almost certainly formed in the disk. And just to complete the story, 13.8 billion years after the Big Bang, that's when intelligent life first emerged on Earth. So it took a long time. You'll notice that I skipped something. I skipped a kind of a big chunk of time here. 9 billion years of mystery. Okay? And, you know, if you went back in time about 30 years ago, we really didn't know the answer to this. We knew that the first stars had to form somewhere, and we knew how old the sun was, and we knew what was going on recently, you know, in the past in the nearby universe. But we didn't know much of what was going on here. And that's what I want to talk to you for the rest of my talk about. About 30 years ago, not quite, in 1990, the Hubble Space Telescope was launched from Space Shuttle Discovery. This would be really the first advanced optical IR telescope that would be in Earth orbit. And this was an amazing thing because it's up above the atmosphere, so you don't have to deal with the atmosphere. You can take beautiful pictures. And I'm sure all of you have seen the beautiful pictures that Hubble produced. And one of the reasons why Hubble was launched and created was to figure out this 9 billion years of mystery that I talked about before. One of the really amazing things that happened with the Hubble Deep Field has to do with this guy, Bob Williams, who was the director of the Space Telescope Science Institute. He was basically the person in charge of driving Hubble and figuring out what to do with it in some broad sense, with a lot of other people. And part of the reward for taking on this very difficult task of running this vast organization, this brand new expensive telescope, was that he got something called director's discretionary time. He could basically point the telescope anywhere he wanted to for a while. And he decided to do something incredibly bold and ambitious. And a lot of people thought completely crazy. He decided to say, he decided to point the most expensive telescope that had ever been built, okay, at nothing for 10 days. This is a big deal, right? Because astronomers fight tooth and nail to get an hour on this telescope, right? He's going to point it for 100 hours at one spot. And the field of view of Hubble is such that if you had a drinking straw that was like 70 feet long, it would be like the hole that you would be looking at, that piece of sky. So he pointed at a completely dark spot of sky for 10 days to see what he would see. And a lot of people said, a lot of experts said, you won't see anything because Hubble is so powerful. You can see so far back in time, you're not going to see anything. What a waste. He said, well, I'm the director. I'm going to do what I want to do. And this is what emerged. So this is called the Hubble Deep Field. This was a really revolutionary image that was created. And it's kind of tiled here because the shape of the camera on the telescope had this funny shape. So this was 1996. And what they discovered is, in fact, this incredibly dark spot of sky where there was nothing there was filled with galaxies. And many of these galaxies were existing billions and billions of years ago, getting close to sort of the very first galaxies that are formed. Right? So there's a lot of stuff out there. A few years later, in 2004, so almost 10 years later, in 2004, there was a revamp of this called the Hubble Ultra Deep Field. And this time they took advantage of a new camera that had been installed by astronauts, sort of souped up Hubble. Advanced Camera for Surveys was installed. And they did a similar exercise and made an even more amazing image. This time the director was Steve Beckwith. So this incredible picture, and I'm going to show you a movie that sort of gives you a sense of what this was. So this is just the spot of the sky where Hubble pointed its lens. And I thought this was going to play. Let's see, here we go. And we're going to zoom in on this dark, see it's a very dark spot of sky. Nothing is there. And suddenly you're going to see this spot that Hubble pointed at. There it is. And you'll see these galaxies. We're seeing them as they were billions of years ago. 10 billion years ago, many of them 12 billion years ago, before the Earth existed. This is what they looked like. And then it runs out. Now, it doesn't run out because we ran out of galaxies. It runs out because even Hubble Space Telescope isn't powerful enough to see beyond it. So we learned a lot of things from these kind of surveys. Not only are there lots of galaxies out there, but as you look farther back in time, you see that galaxies kind of look different than the ones we see today. They're a bit smaller. They're way more messed up. And we think that sort of once you go back about 10 billion years, there really aren't any beautiful disk galaxies like the Milky Way. The thing you think of when you think of a galaxy, right? These beautiful spiral things that I was showing you, right? Those didn't exist about 10 billion years ago. At least there weren't very many of them. And the farther you go back, the fewer and fewer that exist. And so you really get to a point where everything is kind of messed up. And so one of the things that was a little bit frustrating about this is, so I'm very interested in the Milky Way, and I wanted to say, hey, you know, what did the Milky Way look like, right? Because there should be galaxies here 10 billion years ago, 12 billion years ago, that are sort of what the Milky Way should have been like at that time, right? But unfortunately, it turns out that most of the very early galaxies we see, and this I don't have time to go into why, but we understand that most of these early galaxies that we see are going to turn into these massive galaxy clusters like Virgo, and not these things like the Milky Way that we think of as more typical. They're sort of rare objects. The brightest things that exist at those times turn into the biggest, baddest clusters in the local universe. And so this is the one kind of sciencey looking, complicated kind of plot I'm going to show. But basically this is just, but you're all STEM majors, so this is trivial for you. So this is the number of galaxies per unit volume, so the number of galaxies in some big box. And then plotted here is the number of them going fainter. So like there's lots of faint things and not as many bright things. That's what this is saying. And unfortunately, these points are the faintest things you can see in the Hubble Ultra Deep Field. You just can't see anything fainter because it's just they're too far away. And the proto Milky Ways, unfortunately, we think are living here. So we don't know exactly what the Milky Way was doing at that time. Okay. So this flash forwards into something else. So this is 2012. And by this time, the director of Space Telescope was this guy named Matt Mountain. And actually, Matt is a really nice guy. He normally does not sit in this kind of chair and wear sunglasses. But I put this here because just to tell the story, because that's kind of how it felt to me. So in 2012, he called me on the phone and he said, James, I want you to, I've got some director discretionary time, right? And all the other directors that came before, they did like the Hubble Deep Field, and then they did the Hubble Ultra Deep Field. I want to do like some crazy cool thing. And I said, okay. And he's like, so figure out what to do. Do something cool. This is what I want you to do. Figure out a way to see galaxies that are fainter than anything that Hubble has ever seen before. And by the way, the telescope's 25 years old, so it's no young chicken anymore. And I'm going to give you less time than everybody had before to do it. Oh yeah, definitely no money. No money. They spent money, but not. They flew us out there. Nice lunch. So what did we do? So basically, I put together a team of people, and we got into a room with sandwiches and stuff, and we cooked up this plan, and the plan ended up being, I think, awesome. Okay, so that's what I'm going to tell you about. To brag, I'm going to brag. It wasn't my idea. It was many other people's ideas, but it was cool. And I did not name it either. I wish I would have named it this, but they came up with a name, and it's called the Frontier Fields, which I think is a cool name, Frontier Fields, right? So this is the deal. This is what this was. So what we managed to do is use Hubble to see things 5 to 10 times fainter than Hubble had ever seen before. And this is one of the images from one of the frontier fields. And you may say to yourself, well, that doesn't look anything at all like those other images that you showed. And that's because this is actually pointed at a galaxy cluster. We did the exact opposite thing that Bob Williams did. He pointed at a dark spot of the sky. We pointed at a huge, bright spot of the sky where a giant galaxy cluster lived. Why did we do that? It turns out that really massive objects in the universe have a lot of stuff, have a lot of gravity. And we know from general relativity that, in fact, that creates a phenomenon called gravitational lensing. So what these clusters are is they're like giant gravitational telescopes that magnify stuff behind them. So it's almost like we strapped a pair of binoculars on Hubble. We sort of gave it superpowers by using the gravity of a galaxy cluster. And then what happened is, if there are galaxies behind it, those galaxies get magnified and lensed so that we can see them in a way that we otherwise couldn't see. It boosts them. It makes them much brighter than they would have been otherwise. So we can see things that are fainter than you could see otherwise. So this phenomenon of gravitational lensing, you can kind of see it actually. And this is one of the frontier fields clusters. And you see these yellow things here are galaxies in the cluster. So these things are close. But then you see you see this big arc here. Galaxies don't look like that. That's not a galaxy. This is a lensed galaxy. So this galaxy, if you could see it for real, it just looks like a normal galaxy. But its light has gone through this and bent it out in the same way that if you've got a wine glass and a candle, you can play with this later if you want. You hold that wine glass up, and you can see you can make little arcs with the light. This is a phenomenon in lensing, normal lensing that you see all the time, and this is what you also see in gravitational lensing. And so using this power, this sort of power of the gravitational telescope, allows you to use Hubble to see things that are much, much fainter than you would have otherwise, and to count up all those little galaxies that you couldn't have otherwise seen. So at this point, data from the frontier fields has done all kinds of fun stuff. Lots of things that I think nobody thought we were going to see that I can tell you about later. But we began to image, and actually we have seen Proto Milky Ways, finally. And they're fairly numerous, but one of the really interesting things that we found is that, not we, but many other people have found, is that these things are tiny. They're really small and sort of in pieces. And it's sort of surprisingly small how small these little Proto Milky Ways were. So it's kind of a fun story. And there's more to come on the frontier fields, I think. So what I wanted to do now then is quickly just play a movie. So that a lot of the stuff that I do is numerical simulations, and this is one of our sort of newest simulations of a galaxy that we think will emerge and turn into something like the Milky Way. It starts off a very long time ago in these little pieces. And it begins to form this very messed up looking thing, right? It doesn't look like a disk. These little explosions you see are massive stars forming and blowing up. And when that happens, they produce heavy elements and contribute to the rest of the galaxy, and this thing builds up over time. You're beginning to form these so-called dust lanes, and you're starting to see spiral arms here, and now we're approaching about 10 billion years ago. And only at that point do you see the disk. So the disk now starts to emerge. Sometime around here is when we think the sun formed in the Milky Way, and this kind of, once things have settled down a little bit. And at this point, the Milky Way is chock full of complex chemistry interesting molecules, and certainly has the fuel that it would need to eventually make galaxies. Eventually make planets and fun stuff like that. You could not run this on your iPhone, by the way. Not yet. In like 10 years, you probably will. So what's next? So all of this stuff with the frontier fields, one of the goals of the frontier fields was try to do something with Hubble that otherwise we thought we'd have to wait until its successor was going to do. Its successor is called the James Webb Space Telescope. And this is how big the James Webb Space Telescope is going to be. And right now, there's the planned operational date, launch date for the James Webb Space Telescope is 2020. So we've got a couple years. But it's fun to imagine the kind of creative things that astronomers are going to come up with to do with this telescope. And I'd be happy to talk to you more about that later. Finally, I'm going to put my department chair back on now for 1 second. So I apologize. But this is also fun. This is the mirror diameter of the Hubble Space Telescope that sort of made all of these beautiful discoveries that I've basically been talking about the whole talk, right? 2.6 meters in diameter. And we anxiously await the launch of the James Webb Space Telescope, which is going to be 6.5 meters. The bigger the telescope, the fainter things we can see. That scales like the area. The images are going to be crisp, et cetera. It's going to be just amazing. But while pretty much every astronomer in the United States has access to use and do creative stuff with this telescope, Hubble, and will have access with James Webb, and many people in our department use it, including Aaron Barth, who's here today. Something we're very excited about at the University of California is an upcoming telescope called the 30-meter telescope. So this telescope, we think, should be operational perhaps around 2028. We hope it's going to be built on the big island of Hawaii. And it is going to enable incredible things, things that even the James Webb Space Telescope won't be able to do. In certain wave bands, it will make images that are clearer and crisper even than Hubble and JWST. It will be able to look potentially for signatures of life orbiting on orbiting exoplanets beyond the sun, and a tremendous number of other scientific cases that we could imagine doing with it. The 30-meter telescope is a very big project. It's a $1 billion endeavor, ground-based telescope that involves a collaboration between many international partners. But the thing I want to emphasize here is that the partners are the University of California system, so that's us, Caltech, if you've heard of them, that's a small technical school in Pasadena, the entire country of India, China, Japan, and Canada. So we are effectively an equal partner with these countries. And one of the reasons is we had a great donation from Gordon Moore that enabled this to happen, but also because there's institutional expertise in the University of California, because it was California astronomers, UC astronomers, that figured out how to build the first segmented telescope, Keck. And that legacy lives on in our leadership in the 30-meter telescope. And I think UC Irvine in particular is in a great position to lead the world in the kind of scientific activities, creative scientific activities with the 30-meter telescope that have been happening with, for example, Hubble and the frontier fields. You can imagine doing things like that with the 30-meter telescope, and you can imagine those ideas coming out of our campus. So with that, let me say thanks. So one of the really interesting things that we know is going to happen, and a lot of times when I talk about the Milky Way, I'll tell this story. It's pretty cool. The nearest sister galaxy to us is called Andromeda. It's about 2.5 million light years away. But the very interesting thing is it's headed right at us. We know how fast it's moving, and it's basically coming at us at a straight line. And in about 4 or 5 billion years, it's going to collide with the Milky Way. And when that happens, first of all, I suspect we won't be around to see this, but the night sky is going to be cool because there'll be like 2 galaxies. You'll be able to see the Milky Way and then another thing coming in. It'll be very cool, maybe an alien world. And then a few billion years after that, the whole system is going to mix up and to become a big round galaxy called an elliptical galaxy, and most of the star formation will turn off. There won't be many more new stars made. Not too long after, well, sometime after that, the expansion of the universe, we think, is going to be speeding up because of a phenomenon called dark energy. And eventually, none of the galaxies in the nearby universe will be visible anymore. They're all going to be whisked away. And we will just live in sort of a whatever creatures are living in this star system then will be this giant ball of stars, right? And it'll be kind of a boring, weird system, right? Because it will seem like the universe is nothing but a big ball of stars, and it always has been. And so in that sense, you could imagine, right, you could make the case, the time is to study cosmology now, because in this far future, you're not going to be able to study anything, learn anything about cosmology. If you were only living a couple billion years after the Big Bang, the kind of stuff you would have to look through and deal with and looking far back wouldn't be there. So there would be ways for you to peer back into the universe that would be probably a little bit easier for questions like that, questions like the first stars. Just because you'd be a bit closer to it, there'd be less intervening stuff you'd have to deal with. The universe would be a very complex place then. So in some sense, it might even be so crazy it'd be hard to wrap your head around. We sort of live in this kind of quiet time now where we say, oh, galaxies are beautiful disks. At that time, like, it was just nuts. So there's probably pluses and minuses. There's 2 kinds of gravitational lensing effects. One is called strong gravitational lensing, and that's when you get these arcs and these really strong magnifications. That is pretty rare, and you really have to find special systems that are going to be doing lenses, and that's something that sort of you have to search for. It's very rare. But there's another phenomenon that's called weak gravitational lensing, and this is this effect that you're talking about. Like, you have a beam of light that's traveling billions of light years all the way to us. On its way, it gets distorted and twisted just a little bit because there's matter in between. And that does things like it slightly changes the shapes of galaxies ever so much. It doesn't really affect our ability to sort of take stock of the galaxies in the universe, but it provides a way for us to measure how much stuff there is in between those galaxies and us. And in fact, it's an amazing way to sort of map out the distribution of dark matter in the universe and things like that. Yeah, it's a great tool. I should not give the impression that there are not other important observatories orbiting the Earth and many other telescopes all over the world. The Chandra Observatory is a really important X-ray observatory that, again, one row ahead of you, Aaron Barth, has used regularly, probably, I don't know, probably even this year, I don't know, to study different things. That's an X-ray telescope, and it's been important for studying many different kinds of phenomena like hot gas and galaxy clusters and active galactic nuclei, etc. It didn't factor into the specific storyline I was telling today, but it's a really important, great observatory.